Good morning, everybody. This is Jay Foley from Foley Lab. I want to tell you a little bit about our software package that we just released called WPTherml, which is meant to be an easy-to-use computational design engine for materials for harnessing heat. It's written in Python. You can download it from our GitHub page or clone it. There's also a nice little website describing the package. And what I want to do today is just give you a quick demo, hopefully in 5 minutes or less, of how to use it to reproduce a couple of images from this awesome paper from Shanhui Fan's group, which talks about daytime radiative cooling. Basically, this paper describes a multi-layer structure which you can sit in the sun and it will actually cool down a rooftop. It's really amazing, and how it works really briefly is that it's super reflective in the solar spectrum and super emissive in the mid and long IR spectrum, so that actually it can absorb very little solar energy and radiate energy away into the universe. So I'm going to try to show you how to write this, how to get these figures using our software package WPTherml. And I've given myself a couple of cheats so that we can kind of do it quickly. So I'm going to go over to Jupyter Lab, and I have a new file in my WPTherml package. And what I'm going to do is I'm just going to import basically this multi-layer class, which is sort of like the main class in our WPTherml package. And I'm also going to import matplotlib. And I'm going to import something from our package also called datalib, which is going to have things like the solar spectrum data and also the atmospheric transmissivity data. Okay. First thing I'm going to do is actually define my structure, and that's where I'm going to cheat here a little bit. I have basically this complicated structure that Shanhui Fan's group discovered, and so I'm just going to copy and paste those details there. But one of the things I want to point out is that we tried to make this pretty intuitive for you to define your multi-layer structures. Okay. I'm going to specify the range of wavelengths over which I care about the emissivity of this structure. So I basically care about visible and IR. This is a flag that's going to tell me to actually tell the program to actually compute the emissivity at a variety of angles, and this last one is going to turn on some of the functionality of the radiative cooling library. Okay, so now basically all I have to do is create an instance of my multi-layer structure. So I'm going to pass this dictionary that defines my structure to the multi-layer class, and that's going to define an instance of my multi-layer structure. And now I'm also going to get some of this data from datalib. So in particular, I want the AM 1.5 spectrum at all of the wavelengths where I'm computing the emissivity for my structure, and I also want the atmospheric transmissivity data at those same wavelengths. So all the wavelengths that you specify here are stored in a list called lambda array. Okay, so now we basically should have everything that we need to plot these two spectra, because as soon as I create an instance of the multi-layer class, I'm going to compute its emissivity, and I'm going to get this data from the datalib. So let's hit play and let this calculation run. All right, and so let's take a peek. So here we have in the first plot, this is the emissivity of this multi-layer structure across the solar spectrum, and here's the AM 1.5 spectrum. So this looks an awful lot like figure 1A from Shanhui Fan's paper, and then down here is the mid and far IR emissivity of the structure plotted against the atmospheric transmissivity window, which looks a lot like this figure. So basically we calculated these things on the fly just to prove to you that changing a little piece of the structure actually changes these figures. Let's do this. Let's change one of the layers, which is silver, to gold, which should of course have totally different optical properties. And here we go, totally different emissivity in the visible. One of the things that this actually points out is that the mid-IR emissivity of the structure mostly derives from the SiO2 layers, which has some nice absorption in the IR. Okay, and one other thing that we can do real quick, since we use this cooling lib, we're going to actually calculate quantities like the total power emitted from the structure. So let's actually just print out some of those values. Okay, so this is actually the total power emitted by this structure. Let's run this whole thing again, silver, and see if that number changes. Should change just a little bit. Okay, so it changed a little bit, so a little bit less power radiated when you have silver instead of gold. So this is basically telling you how much power is thermally emitted by your structure, and so that's actually a power flux which will cool things down. We can also look at how much is absorbed from the sun, so we can say print absorbed solar power, which is warming, is, and that's stored as another attribute of our structure, which is called solar power val. And one of the reasons why I wanted to show you this is to emphasize that all the quantities, at least as far as I can remember, should be in SI units. Okay, so this is a power absorbed, solar power absorbed by the structure, and watts per meter squared. So that's actually really low. If you remember the actual total solar power, integrated solar power density from the AM 1.5 spectrum is like 1,000 watts per meter squared. So this is telling you this is a very, very good structure in terms of not absorbing a lot of solar power or being highly reflective. Okay, so anyway, that's just a little demo of some things you can do with WPTherml. Please check out our software, go to the web page, clone us on GitHub, let us know if you find any bugs. All right, enjoy.